The goal of this project was to program a given robot to give it the ability to autonomously map and navigate throughout an environment. The robot needed to navigate around the environment to predetermined waypoints while avoiding its mapped objects.
This robot uses a LiDAR sensor to measure the distances to its surrounding objects. It then uses this information to navigate its environment and avoid obstacles.
In addition to avoiding walls, the robot had to be able to avoid other dynamic obstacles. Here you can see the robot approaching a remote controller in its path. It observes the object and plans its path accordingly to move around the object.
The robot models its environment as a grid of spaces which hold representations of what occupies that space in the real world. Each grid cell of this occupancy grid is 5 centimeters by 5 centimeters. The black and gray squares are areas where the sensor has detected an obstacle, and the darkness of that square is the probability that an obstacle exists there, based on the number of sensor readings returned from within that square. The white spaces are the areas that have been detected as clear by the LiDAR sensor, and are therefore areas where the robot can drive. The yellow spaces are unknown areas, unscanned, or behind a wall. The red areas are extended from the obstacles and represent areas where the robot may impact an obstacle, and therefore the areas that the robot must avoid. The light blue squares are the robot's path, while the dark blue is the robot's current idea of where it is in the world. Finally, the green squares are the waypoints that the robot is attempting to move to.
The robot generates its path using Dijkstra's algorithm. The algorithm calculates a value for each square that represents the distance from that square to the goal. The robot can either move in the 4 cardinal directions, which are given a weight of 1, or diagonally, which is given a weight of 1.4. The algorithm starts at the goal with a value of 0, and assigns values to its neighboring squares, continuing until the start square is reached. The path is then generated by following the gradient backwards from the start back to the goal. This will generate one of the shortest paths between the start and the goal, though not necessarily the one with the least number of turns. The robot will rescan its environment at each turn, or every 10 grid squares for long path segments. These paths are shown as the light blue squares in the map. After each scan, the robot will update the occupancy grid and determine if its path was blocked. If it is, the robot will calculate a new path.
The robot also uses a localization algorithm, where it uses its LiDAR distance data to fit its local map to the global map. By determining which orientation and location the robot is currently in based on this sensor data, the robot can correct any error that may have occurred while driving, to avoid misplacing itself and missing the waypoints. This is especially useful as the table's environment sometimes causes the wheels to slip, confusing the robot as to its current location.
Here we can see the robot navigating the waypoints marked on the course. Each waypoint has been placed in relation to the starting location. The robot scans its environment and moves along the planned path to that waypoint. There are a total of 5 waypoints that the robot is navigating to, while building its map of the environment and using that map to correctly position itself. After the robot reaches the last waypoint, it turns to return to the starting location. While it chooses the best path possible based on previous data, it continues to scan as it moves back to account for any possible changes in the layout of the world.